Hey guys, we just started. Guy, we're live right now. Can you actually unmute? Perfect.
Hello. Yep. Can you hear me?
Yes, audio is great.
Perfect.
Cool. Feel free to get started.
Okay. Hello, everyone. My name is Guy Zyskind. I'm the CEO of Enigma. Enigma has been building privacy solutions for quite a few years. In the last year, we've become a core contributor to Secret Network, which is focusing on building a privacy preserving blockchain. And today I'm going to tell you about building private smart contracts with CosmWasm, which non-coincidentally happens on Secret Network. So let's get started with a brief introduction of Secret Network. Our mandate is to drive adoption and usability of decentralized applications and blockchains by solving the problem of on-chain privacy. More concretely, Secret Network is really a blockchain that allows you to run computations over encrypted data. And the main idea is to bring privacy to smart contracts. You can think about this as Ethereum, but with encrypted smart contracts that give you absolute privacy. Some nice facts about the networks. Secret Network is the first and right now the only blockchain that gives you privacy preserving smart contracts. And I will use privacy preserving smart contracts or secret contracts interchangeably, but these define the same thing. It's built on Cosmos SDK, which means that we use tenement consensus as usual. We have a native coin called Secret. As usual, it is used for staking, for delegation, for governance, and to pay transaction fees. And the secret contracts engine, as this talk describes, are based on CosmWasm, which means that the smart contracts are written in Rust and they compile down to WebAssembly. The unique part in Secret Network compared to other chains with CosmWasm is that the contracts themselves are completely encrypted, which means that inputs, outputs, and state transitions are completely encrypted. And the way we do it is we use a combination of secure enclaves with key management and encryption protocols that help achieve the privacy features. So from a bird's eye view, the way that this works is you have a secret contract deployed on the network, and then a user can interact with this contract by just sending a transaction to execute the contract. But the main difference is that the user on the client side encrypts their inputs completely in a way that the nodes can operate over those inputs but not actually see them. This is done by the nodes running what's known as a trusted execution environment, or TEES. The state itself is also encrypted. So if you're observing the chain and you're trying to read through the chain's history, all you're going to see are really encrypted blobs. And then the contract outputs can be sent back to the user encrypted with a key that only the users know. And that way you can also maintain output privacy. One thing that I didn't mention, I'm running with one screen, which means I don't see any questions. So I advise everyone who have questions throughout the talk to pose them, and in the end, I will, leave some time for questions. All right. So moving on, let's, switch gears a bit. How does it work? So a big piece of what we're relying on is what's called trusted execution environments, or TEES, as I mentioned. TEES are basically hardware-enabled secure enclaves. And inside those secure enclaves, really what's happening is that you can ensure that data cannot be observed from the outside, which means you get privacy, and data cannot be tampered with, which means that you get correctness. Now, this includes the host itself. So even the host of the machine, and even if that host has root access and even physical access, it cannot see anything that's happening inside of the secure enclave or tamper with it. This is an extremely, extremely strong adversarial model. And actually, this could help us tackle any Byzantine behavior, with the exception, obviously, side channel attacks and other things. But assuming that you trust that it is secure and robust, then if you develop the right protocols, then you can make sure that no adversary, even if they have full control over the machine, can actually see what's happening and break these properties. But on a high level, it seems like this solves everything, but not really, right? There's quite a few challenges, and there are even more challenges when trying to deploy this kind of technology inside of a decentralized network. So first of all, yes, in the secure enclave, things are trusted, data is protected, but how do we get the data and how do we get code for execution into the secure enclave? Remember that the host of the machine controls everything else. And specifically, it controls all communication with the enclave itself. Okay, that means the ins and outs to the enclave. And what's even more troubling is that because this is a network with consensus, and remember that all nodes are running these keys, then we need to make sure that all executions are deterministic, because consensus cannot happen with random results. All of the nodes in the network need to agree on the same blobs of data, which basically implies deterministic execution. So we need to find a mechanism to get data in, and again, that data has to be encrypted from the outside, and we need to get encrypted data from the outside into the enclaves in a way that maintains deterministic execution throughout the process. And that is very challenging. And the last part is we need to ensure that no one, and I mean absolutely no one, not even one node in the network, can actually fake it that they are running an enclave which is not genuine. Because if one node can run an enclave that is not real, then they can get all the data and they can decrypt it in the clear, and it's game over. So the way we solve this on the protocol level is first we build a protocol for provisioning shared secrets. And what that means is that all of the nodes basically get to a position where they all share the same keys inside of their enclaves, but those keys have never been observed outside of any enclave. And the way that this is done is basically sequential. So the first node in the network joins in and then generates a true random seed inside of its own enclave. Enclaves have a mechanism called remote attestation. Remote attestation is, from a practical standpoint, it's kind of like zero knowledge proofs, but it is much, much simpler and has different security guarantees. But the main idea is that I can prove or I can attest to any outside observer that I ran some computation and the result of that computation is ran inside of the enclave and I did not observe it and I did not tamper with it. And that's exactly what we're doing. And using the remote attestation, we can actually validate very efficiently on-chain that a proper random seed was generated inside of this first node's enclave. And then any subsequent node does something similar, but instead of generating a random seed, it generates an encryption key that other nodes can use to encrypt the seed back to it. So what happens is I'm a new node. I generate an encryption key. I generate a proof that this encryption key was generated inside of the enclave. I post that on chain. Other existing nodes view it, validate the proof, and then re-encrypt the original seed and share it back to me. And that way, we provision the same seed across all nodes in the network. Now, using this seed as a source of pseudorandomness, we can actually derive any number of keys deterministically and basically ensure that the network maintains its consensus and deterministic invariance. Now, this is a gross oversimplification. If you want more details, I suggest you look at the link below. It has all of the spec details. Okay, so once the secrets are provisioned, now using some key derivation and some other techniques, basically users can encrypt their transactions, their contract executions to the nodes. And then from each node's perspective, when it gets an encrypted transaction, it basically pushes that into the enclave where the computation actually occurs. Now, one important thing to notice is that this is all CosmWasm. Throughout, this is Cosmos and CosmWasm. But in order to allow CosmWasm contract execution inside of an enclave, we really had to do a lot of work and redevelop a lot of the interfaces and actually switch the WebAssembly backend and really do a lot of work to make it operate with the constraints that secure enclaves demand from us. But it is working, it's live, it's tested, and it's been working for a while. Another thing to notice, and I think that is the really interesting part, is enclaves are quite limited. And these are stateful computations, right? There's state involved. And so it's not just going into the enclave, running the computation securely, and then going out. Remember that throughout execution, you may want to read from state, which is the persistent memory, or write to state. And for these, you have to go in and out of the enclave. And this is where it gets really challenging because, remember, everything outside of the enclave is completely untrusted. It's completely malicious. We have to assume it's completely malicious. So we had to really, really make sure that the protocol protects against any leakage, any tampering when you go in and out to do these reads and writes. Okay, so let's move beyond the protocol level. Let's see what we can build. And it turns out that you can build quite a lot of things on Secret Network with these privacy-preserving CosmWasm contracts. And this is a short list of things that have already been built or currently being built as we speak. So all of these are either live or about to be live. And I think the first and maybe the most impactful application is privacy tokens, or again, interchangeably, we call them secret tokens, which are basically tokens very similar to ERC20s, except that they give you the privacy guarantees of a privacy coin. So you get the benefit of the ability to program these very easily and deploy these very easily like ERC20s, but at the same time, you get the privacy guarantees that you would with things like Zcash and Monero and so forth. Now, combining that with an Ethereum bridge that we build, and that bridge can actually be extended to other chains, we can actually bring assets from different chains and then create corresponding privacy tokens from them on Secret Network. And another very useful application that is currently being worked on is a secret AMM. Other than being privacy preserving, because all of the transactions to that AMM are completely encrypted, it means that it would be also a front-running, maybe even the first front-running resistant AMM out there. And as many of you know, that's a big problem in Ethereum. That's a big problem with decentralized exchanges and Uniswap in particular. Other use cases we've seen include secret vaults, which are basically ways to keep decryption keys or encrypted data inside of a contract, and then through have some programmable conditions, like if you pay enough money, then you get the encryption key to decrypt this secret NFT or this data set or whatnot. Other use cases are on secret on-chain voting, which is, as we know, very important to prevent attacks like bribery attacks, lottery, fair lottery, and confidential auctions. All of these are very, very important use cases that are not available on public blockchains as it is. Now, one thing to mention, and I know I'm preaching to the choir, we built an Ethereum Bridge, as I said, that allows you to bring assets from Ethereum to Secret Network, which basically means that you can lock, let's say, ETH or Link or DAI or whatnot on the Ethereum side, and then you would automatically mint a synthetic secret token, which is basically a CosmWasm secret contract, which essentially takes these Ethereum assets, and again, this can be generalized to other chains, and provides them full privacy at a fraction of the cost of what's available today. And this is coming live this week and going to support all of the major Ethereum assets and probably other assets as well. Now, one note about this, I know, this is Cosmos, this is the Interchain. We are fully aligned with that vision, and we expect to extend this mechanism to PEGI, to IBC, once these are available. But in order to bring privacy to these assets and these chains today, we were tempted to just build something quick that is secure enough on our own. Now, I wanna dig deeper into the privacy tokens aspects and how they develop. And the reason I want to do this is because they're extremely useful and cool, but also I think it's a great way to illustrate the challenges in building privacy-preserving smart contracts. So if you think about Ethereum first and smart contracts in general, people used to think that it's very, very simple to build these contracts, and it's not, you don't have to spend a lot of time, you just have to make it work. But as we've seen from so many smart contract vulnerabilities, actually building safe smart contracts is very challenging. And you can extrapolate that to privacy as well. The thing is, with privacy-preserving smart contracts, you really have to think about what you're doing to prevent any unnecessary and unwanted leakage of data. So let's take secret tokens as an example and see how they operate. So when we went ahead and tried to build the spec for secret tokens, and we call it SNP20, not very original. SNP stands for Secret Network Improvement Proposal, and 20 is, from ERC20. We naturally took the obvious step of taking the ERC20 spec and try to, build our own spec from that. And as soon as we started reading the ERC20 spec, you can see that, obtaining a balance is completely public. Like, it's not meant to be private in any way. And in fact, ERC20 assumes throughout that balances are public, transactions are public, and all the information is out there. And wallet providers, need it. It's a necessity throughout. So we thought very hard about how to solve this. And the naive solution was, let's just make all balances encrypted. And then let's allow each user to sign a transaction, something like get balance, which allows you to retrieve your own balance, but no balance of anyone else. So you can only retrieve your own balance, but you need to send a transaction to do that. So on a first glance, I mean, this seems like a perfect solution, all we need. But it turns out that this is not quite as simple as that, because once you dig a bit deeper, you realize that there are quite a few problems with it, primarily with both cost and usability. And actually, I would argue that if we have developed it that way, no one would use it. So first and foremost, I mean, are we really going to ask people to spend money anytime they want to query their own balance? There's no ERC20 token that works that way, no spec, no coin that works that way. This should be free. And even more importantly, a lot of people use things like hardware wallets, where it's considered bad practice to actually connect your wallet just to read your balance. Like that should be done completely independently of actually using your private key. And the second problem, which might actually be more problematic, is that how would you know when someone sent you money? And how would you keep track of all the transactions that you send to other people? That kind of accounting, which is obvious and given for granted in every wallet, in every wallet software, becomes extremely tricky and probably unusable in this situation. So what we came up with is this idea of read-only viewing keys, which allows you to share a key that can only read your balance and transaction history with, for example, wallet providers. Now, just to be clear, you don't have to compromise your privacy with wallet providers. Wallet software can integrate the ability to create viewing keys locally and store it locally, maybe only store an encrypted backup on their servers, but it doesn't again mean that you need to compromise your privacy. Now, the takeaway message here is that a lot of the things that we take for granted in public blockchains are made easy because the ledger is public. When you have a privacy chain, you really have to think hard about how not to leak data and how to, properly design the contract so that it makes UX super friendly and very usable. So to summarize, in a standard web application, and I mean a Web 2 application unrelated to blockchains, privacy is really taken for granted because you have a trusted third party, they protect the data. This is really, bad practice. None of us like this. Part of why we're in the blockchain space is because we don't believe in that model. But at least, unlike with public blockchains, there's only one entity that sees your data, not everyone everywhere. The second thing is that getting privacy on public blockchains is actually harder than it seems, both on the protocol level and the application level. You can't just copy paste a smart contract and expect and publish it, deploy it on our network, and assume that it's going to be privacy preserving. You'll probably have to be proactive about it. That said, this opens up so many possibilities that are not available in blockchains today. And we would argue and hypothesize that without solving for privacy in public blockchains, there's a glass ceiling for where blockchains can get. It cannot get mainstream adoption. It cannot get the public's. It cannot get the public to use it, whether it's retailers, or institutions or organizations. And the last and most important piece is Secret Network is live now. It's the only network that is live now and provides this functionality. You can develop CosmWasm compatible contracts on it. So if you've used CosmWasm before, this should be extremely familiar to you, and you can probably take your contracts and just make privacy-aware changes to them and deploy them on Secret Network. And also, secret tokens are live, and we've seen people, even non-technical people, deploy new secret tokens, and we've it's only been available for like a month and a half, and we've started seeing more and more of these. And now with the Ethereum Bridge coming this week, you'll also be able to import assets from Ethereum and soon to be other chains, and turn them into secret tokens on Secret Network. So I'm gonna open this up for questions. I'm gonna take a look, see if there's anything. There are quite a few links that posted in the last slide that you can see. Okay. All right. So first question is: currently, all nodes perform computation, which increases the attack surface. Will you be able to eventually have the protocol randomly select 20 nodes to perform computations and therefore minimize the attack surface? This is actually a very, very interesting proposal. We've spent weeks, I think, debating this. And in the end, we decided to go with simplicity, which is why all nodes replicate this ability. The way we think to tackle this is, yes, either we move into more of a sharded approach, but we're in the Cosmos ecosystem and we think we should tap into that. And essentially the best way and most natural way we see in solving this is probably to maybe build side chains that are just like, take the secret network code, potentially integrate the token into them somehow, like we haven't thought about that seriously, and then connect through IBC to the main secret network. That's probably the best way to solve it. Let's see. How do you support traceability of bridge tokens, Ethereum tokens made available as secret synthetic tokens? I mean, you can see everything that's locked on the Ethereum side because Ethereum is public. But then once on the secret side, when people transact on it, like if you have a secret ETH on secret, we will be able to see the transactions that happened, but all of the information would be private. The only thing we can track is eventually deposits on Ethereum and withdrawals, because that is public, and that's probably a desired functionality because it gives us interesting aggregate statistics. One more question: is Enigma team actively trying to crack their own privacy model? I think that's a very, very interesting technique. We're trying to just use best practices to protect against side channel attacks, but we haven't tried to actively crack it. We do invite people to try and use responsible disclosure, and we are more than happy to provide bounties for successful attacks. I think that's it. Let me see on the main chat if I see anything. Nope. Cool. I think we're all done.
This was perfect timing. We're going to transition to the next session now. Thanks again for your time.
Thank you very much.